Hello, and welcome back to AMAT502, Modern Computing for Mathematicians, here at the University at Albany, SUNY. Today, we're going to continue some of the same topics we've already discussed, notably revisiting how functions work and continuing trying to understand that in greater detail. We're also going to get to one of my favorite topics in all of computer science, that is that of abstraction. What does it mean to write functions that can be used in a way that's abstracted from one another? And we'll finally conclude with the way in which functions can be used to recurse on themselves. And this generates some of the most beautiful patterns in mathematics and computer science. Some of the other things we'll be getting into include issues of keyword arguments, default values, docstrings, and of course, my favorite application of recursion will be the Fibonacci sequence and the golden ratio. So just a quick reminder, a function, you have the keyword def, or at least a reserved word def. Whatever the name of the function is, cannot start with a number. And then a list of formal parameters separated by round brackets and abstract variables like x, y, z. Once you've declared that first line, which defines the name of the function, along with its list of formal parameters, you can put indented a body of code, and that can be any piece of Python code. So the important thing to remember is how is a function evaluated when you come to actually call it. So, for example, if we use f of x, y, z, w with some list of parameters, when we write the definition of the function, we can just use these abstract variables that haven't been defined yet. This is this notion of a local variable. Its scoping completely exists within the function. It's not used outside of it. So you can reuse letters for whatever you like. If you have x used somewhere else and then you want to use x here, it might be okay, but better to try to avoid reusing variable names. Anyways, when we go to call that function, we have to pass actual values. That means that instead of just using things like x, y, z abstractly, we need to give objects with valid data types in Python. These values can actually be commands as well. So, for example, 2 times 3 might be fed as a value, and that's the command of multiplying 2 by 3. The formal parameters used to define the function are then bound to the values that you pass. These are the actual parameters. And then the point of execution moves from a list of parameters to the first line of the code body. Code is then executed line by line until either a return statement is reached, in which case the value of the expression following return is the value of the function. Alternatively, you could write a function which just prints but doesn't actually return anything. And it's important to understand the difference between the two. Print just tells the computer to display something on the screen, whereas return returns a value which can then be used by other functions. We saw this last time. So, for example, in my do nothing function, even though I give it a parameter x, it doesn't really do anything. Let's just test to make sure that I can do what I claimed earlier. So I can bind x equals 2, and let me see if I can also do this. Okay, so notice this illustrates this notion of scoping. Even though I define x to be equal to here, I can reuse x as a formal parameter in my do nothing function, which I've now changed to actually do something. And if I call do nothing with 4, it binds 4 to x and returns that value, exactly as the function said, even though I'm reusing the word x or the variable x. That's because x here is being used as a local variable, but that x also simultaneously exists as a global variable. So just to see that. All right. or I can do both, and then also print. Okay, great. So I've shown that you can reuse x because x is a local variable and a global variable. But again, you should think just in terms of math function. When we talk about sine of x, it doesn't have any specified value until you actually want to compute sine of something. All right, so let's try to understand this issue of argument evaluation a little more carefully. So normally formal parameters are bound to actual parameters, and you, again, usually work from left to right. So if I have 4 arguments, x, y, z, w, and I pass 4 values, actual parameters, for the string cat, the Boolean false, and the integer 10, it knows in what order to bind those values. X is going to go to 4, y is going to go to cat, z is going to go to false, and w is going to go to 10. All right, so let's see how this works in our Mad Libs example, which if we read the code carefully, first there's an if statement, but I've got a number, animals, case number 2, and then assuming case is true, which it tests identity using double equals, I'm going to return the string my number 1 animals always kiss me number 2 times. And then in the case of this is not true, always kiss me is replaced with never kisses me. So as you can see here, if I kiss me 2 times. Calling the function, there are 4 slots to give actual parameters, which we gave 10, cats, false, and 2. And it used it exactly the way we expected it to, where number 1 was 10, animals was cats, case was false, and number 2 was 2. But Python also gives you the ability to pass arguments in any order if you use the actual formal parameter name. So let's see how that would work here. So earlier, when we called the Mad Libs function, just to remember, we put animals in the second slot. But here, we're going to put animals in the first slot. But we can do that because we actually explicitly tell our function that I want to use animals, that's my argument, my keyword, and bind it to the value dogs. And then similarly, I can let number 1 be 23 and number 2 be 41. And I can let case be false. And you'll see this actually executes just fine. Just compare. Back here, we had number, animals, viewed as a string, a case, which was a Boolean, and another number. Here, we've passed it in a different order, but we can do that because we've used the actual keywords that were used to define the function, meaning animals, number 1, number 2, case. All right, so there's another thing you should be aware of with Python, and this is something we've already seen, as we'll point out. So you can also set certain variables to have a default value, which means that you can pass fewer arguments to the function. In our Mad Libs example we just looked at, there were 4 arguments, so 4 different things you could pass. But we could actually get by passing 3 or fewer if we make some of those variables have default values. One thing to note, caveat lector, this means reader beware. Once you've used one variable and given it a default value, then all the other following variables also have to have default values. So I'm going to rewrite my Mad Libs function so that I've got my first number of animals, the actual animals viewed as a string, a number 2 animals, and then I'm going to go ahead and write in the definition of my function that this variable case has the value true. What that means is that if I don't, as a user, give a variable that will be bound to case, it will automatically assume that case is true. All right, so let's see how this works. All right, so case is true. This means it already initiates this case. And in that case, it's like my number of animals kiss me so many number of times. And notice that when I call madlibs2, I only give it 3 parameters. That's because it assumes that the additional parameter case already has the value true. But I could also override this, oops, by changing the argument and now supplying it by saying that this is false. So notice I've been able to change the number of arguments by giving it a non-default value. But if I don't supply an argument, it's going to assume that it's always the default value. You might want to think about when you're writing your functions, most of the time people want to assume certain things, like the step size is 1. Which gets to this class question. And I already tipped my hat. So we already considered a function that had default values. This was the range function. We had a start value, a step value, a stop value, and a step size. And notice we made the step size the 3rd argument. And if we didn't give the 3rd argument, it assumed the step size was 1. So this showed also the principle that when we order our arguments, if we want some of them to have default values, we have to put the things that have default values at the end. And indeed, the most primitive version of range, where you only supply 1 argument, assumed you just had the stop value, where it stepped automatically at, started at 0 and then moved on to b-1. All right, so now that I think about it, actually, you just have to, there is an example where they actually had things in the reverse order. All right, but either way, let's go ahead and move on to our next topic. So we've already used a couple times in this class the hashtag symbol to provide human readable commenting. So definition of the number of times x, y. We want to say, oh, this is going to be the function that returns y times x, where I usually assume that y is an integer and x is either an integer or maybe it's a string. Now, the only way in which you can actually read that comment is if you have access to the source code that went into writing this function. But it turns out there's another nicer way of encoding how you should use a function. And that's using something called a docstring. So a docstring is something you write at the top of your function body where you surround a description of what the function does using 3 double quotation marks. So 1, 2, 3, some sentence, 1, 2, 3, double quotation marks. So this is a kind of a really appealing use, as I'll illustrate just shortly. So suppose I want to be a little nefarious. So I've written a function num times, which essentially does what I just said. But you can put literally anything you want here. Why do you want to know? One of the reasons why these docstrings are useful is that sometimes you might want to hide your code body. But nevertheless, a user who wants help to know how to use your function should be able to use help and then the name of your function. And Python will go ahead and give it some basic details. It says, okay, it exists in your main body of code. This is technically something that comes from object-oriented programming, which we're going to understand in a few more lectures. But nevertheless, help essentially returns whatever in the docstring. So if I were to change this to my docstring, I called help, it would give me that basic information about where this this function lives in my module. And then it also provides whatever I coded up in the docstring. All right, so here's some other things you should know. So sometimes if you have a function, you don't know what to do with it. You don't even know what parameters to pass it. If you just type in the name of the function, you hit Shift-Enter, it's going to give you some very rudimentary information. It says, okay, this is a function. Again, it lives inside this main code body. This is our main class. Once we get to understanding what classes and subclasses are in the sense of object-oriented programming. But it at least tells us how many formal parameters num times takes. Now, by contrast, if I step back a little bit and I copy this, what was normally a comment, move up, and I'm going to make my docstring more informative, where it says something like, this function assumes x is a string or int and that y is an int, and then returns either y copies of x or the integer x times y. Right? This feels like a much more helpful function. So I'm going to go ahead and now store this definition of my function num times and its docstring in memory. And again, if I do this, it still tells me something only sort of useful. All I know is that num times is a function in my main class, which has 2 arguments. But instead of using that, I ask, help, what does num times do? So it does some very nice things. It, in a more human-readable format, says, num times is a function inside my main module, main. It operates by having 2 formal parameters, x and y. And then it generates whatever was stored in my docstring. And so it tells the user how to use num times. So one thing which we'll get to more, and this is, I have to say, a topic which is less useful when we are working with Jupyter notebooks. That's because Jupyter notebooks already have a form of generating errors. But that said, if you write larger code, you want to be able to maybe supply a more robust set of test cases that also generates messages when you've entered in the wrong input. And for example, one of the most basic things you might want to do in your function is type checking. Make sure that your user is using your function in a way that the function is meant to be used. So if I were to exaggerate num times, again, I'm assuming how I want it to be used is that x or y, that x is a string or integer and that y is an integer, and then returns either y copies of x or the integer x times y. Now, one way in which you can surround or test your parameters for if statements is you can go ahead and put another if statement inside your function, which says if type of x is equal to the string equals equals, or type of x is equals to int, and I'm going to make that my or statement, surround that by parentheses, and I always require that type y is an integer. Then I'm going to actually do what I want my function to do. I'm going to return y times x. And in all other cases, so where those things don't, or that Boolean expression doesn't evaluate to true, I'm going to return an error message, which I'm just going to do as a string right now. Return error message. This function accepts 2 arguments. The first can be of type int or string. The second must be of type int. So this is meant to prevent large bodies of code where you write functions which are supposed to be used in very particular ways. Prevents them from being misused, and so that you don't end up, say, causing your function to loop forever. So writing good, robust code, which is able to ward off or at least encourage users not to do anything dangerous, is a good thing all programmers need to learn how to do. All right. So now we get to one of my favorite topics in computer science. This also gets at the question of what does it mean to really use a function? How do we use it properly? One of the topics which I really loved learning about as an undergrad was the notion of abstraction. to refer to our MIT book here by Guttag. Abstraction is the true art of programming. Of course, there's another book which really, I think, helped explain this in greater detail, and that's the book by Gerald Sussman and Hal Abelson called Structure and Interpretation of Computer Programs, sometimes called SICP, S-I-C-P. So what is abstraction? Abstraction is the art of creating appropriate containers of information that can be referred to at higher levels without needing access to the information inside those containers. Essentially, you don't want to bother people with implementation details. Just want to tell people how to use their software, how to use your software that you're writing, or use your code, so that they don't have to get too bogged down in the details of how you decide to implement things. The sort of language which you want to hear is that we use abstraction to reduce functions to these sort of black boxes, inputs, and then we generate outputs. Don't really care about what's inside the box. All we care about is when we put something in, what comes out. So last lecture, we did two different implementations of the square root function using really primitive operations like multiplication, exponentiation, subtraction, and a while loop. And we gave two implementations, one using this sort of linear search where we just stepped through linearly until we got to a value which best approximated, or at least got to within our tolerance of the square root. We also gave a much more efficient implementation which used bisection search. The first one was something that operates in linear time. The second one was one that operates in logarithmic time. And so logarithmic time is much faster, much better. So point is, if you're coding up a lot of different things, and even as we start to use built-in functions in Python, we don't really want to know how they chose to implement, how to take the square root of a number. All we care about is using it. So that's already one example of abstraction. But I want to encourage a much broader perspective on what abstraction is. This is just something that's really good practice for programming. In particular, it's going to allow you to write large bodies of code with hundreds, if not thousands of lines, where you don't end up stepping on yourself, where you say use a variable name somewhere, maybe wasn't defined locally, and then you end up reusing it. And then when you go to run all your code, you start getting things you don't understand because, oh, actually you reused a variable name here, which then got bound and stored in memory. It can create all sorts of problems. So there's also and just on that practical note, I'll say that if you ever watch, shows like Silicon Valley, you'll see that very often as a startup, even if you're doing something relatively lean, you're gonna probably have to collaborate with programmers, which means you wanna be able to write your code in nice self-contained ways where internal specifics of how you implemented it is something your teammate doesn't need to know. So it's just a good practice. And it's very much necessary if you're working with a large group or even just a small group, even just one other programmer. Additionally, I like to think of abstraction as a philosophical concept, which is important to think about. So, we live in a society where people have different specialties doing different things. I trust that my doctor, when they prescribe me a new medicine, can tell me, how it works, what are its side effects, things like that. But I'm not going to necessarily ask my doctor to explain on a deep level how these chemical reactions occur in my body and produce the effects that the medicine's supposed to produce. And that's those specifics of how those chemical reactions occur. You can tunnel down, go farther down the rabbit hole and ask, how do I explain these chemical reactions in terms of basic principles in quantum mechanics? You start to see how a very basic thing like taking an aspirin, if you wanted to be annoying about it, could recurse down until you're asking someone about the finer aspects of how do chemical reactions occur, period. And so we want to be able to abstract and say well, I'm not going to pretend to explain to you how quantum mechanics works. I'm not going to explain to you what chemical reactions happen. I'm just going to say, if you take this Tylenol or this aspirin, your fever will reduce. That's something where you've abstracted away the details. Other examples, again, ones that are very relevant to today. An epidemiologist or a public health expert might only want to know about the people who are going into the hospital for breathing problems. Again, when I wrote these slides, this was back when we were having the vaping epidemic. But now, of course, due to coronavirus, that's another issue where people go in with breathing problems. We don't necessarily want to know what was the specific diagnosis. We just want to know broad metrics, like how many people went in with these complaints, where the people who are diagnosing and documenting these complaints are doctors who understand biology of the human body, but maybe don't understand quantum mechanics. We have to be able to abstract our responsibilities and our knowledge so that we can work in this really complex society. All right, final topic for today is recursion. So we already mentioned several ways in which looping programs can exist back in our second lecture. We talked about while loops, for loops, and then we alluded to recursion. Recursion is definitely one of those things where it stresses how you understand how the program or how a program is interpreted by Python, especially when you are defining something in terms of itself. We've already seen examples where we can increment or decrement a variable by essentially calling itself and then adding or subtracting one. But in math, we also use recursive functions all the time. So for example, in factorial, which is the product of all the non-negative integers from n up to, from 1 to n, is an example of a recursive function. And in fact, the way you can define in factorial is to say it is n times n minus 1 factorial. Well, then you might say, well, what's n minus 1 factorial? And then you put that on the left-hand side here, and you say, well, it's n minus 1 times n minus 2 factorial, and so on and so forth. Eventually, you have to stop somewhere. This is where you provide a base case, where we just declare that 1 factorial. We also usually declare that 0 factorial is equal to 1. So that's an example of recursion in mathematics. All right, so one of the things we'll do as part of our active learning exercise is to make sure everyone really understands how to program their own implementation of factorial. I'm going to have you all go ahead and program a recursive implementation of factorial, provide with it a docstring, and also provide some nice if tests to make sure that someone doesn't try to take the factorial of, let's say, a cat, where cat is a string. All right, so we'll do that in class, but you can all think about it right now. All right, so moving on. What's the difference between a recursive and a iterative implementation? Well, one is one where we don't really need to call the function itself. So standard implementation of factorial is where you just go ahead and use the definition I alluded to in words, which is that in factorial is the product of all the integers from 1 up until n. So this means you can create some sort of initialize some total variable and also initialize some sort of counting variable. And then just remember that you would take total to be total times where you are in this counting process. And you're gonna go ahead and step through this while loop as long as j, your counting variable, is less than the input n. Total is then increased by multiplication by j, and then you increment j so that eventually this while loop stops. And once you've done stepping through that loop, you return total. Recursive implementation of factorial is going to look much shorter, so I hope you appreciate that. All right, so let's get to another example of a recursive sequence. So Fibonacci sequence, one of the most basic examples of a of a recursive sequence that we usually learn in math. So you want to know the nth Fibonacci number. It's defined recursively as the sum of the two previous Fibonacci numbers. So what this function does is, well, first it checks, after writing in your docstring, whether or not you're at one of our base cases, or n equals 0 or n equals 1. And again, equality is tested with two equal signs. In that case, you return 1. That's our base case. Everything gets built off of that. But assuming you want to know, let's say, what the 15th Fibonacci number is, you're going to be in this else clause, in which case you then call the function itself in two ways. One where you've called the function fib, which is the function we're defining here, but with one less argument. But we also add fib, again, the function we're defining, where we've called it with two less as the argument. So now using an actual code block, let's see, I said, what's the 15th number, 15th Fibonacci number? It's 987. So notice, even though this appears to be a circular definition, where you're defining a function in terms of itself, because you're changing the argument, it's not truly circular. And in fact, we know that it's going to provably terminate because we decrease our argument values until we reach our base case. So this eventually becomes well-defined. And of course, we want to go Fibonacci 3, 4, so on and so forth. All right, well, this seems pretty slow, having just like enter in Fibonacci numbers. That's why I want to get to a quick aside on, suppose you've written a function, you want to actually test that it does what you think it should do. So one very good thing to do is to actually test your functions by writing another test function. All right, so how would that work in this case? And again, here we're assuming we've properly abstracted, so meaning we've black boxed our implementation of fib, and now we're going to test it in a different code cell, or maybe even the same code cell, but be able to call it separately. And if we've really done abstraction properly, one of the things that will happen is that we could change, let's say, the implementation of fib, but not have to rewrite our test functions, because we're hidden all the implementation details. All right, so in this test function, I'm just going to go ahead and consider printing a bunch of Fibonacci numbers using a for loop. All right, so here we go. I've got my Fibonacci, and if I were to go ahead and test fib, get the first 12 Fibonacci numbers, you'll see I get the standard Fibonacci progression: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, and so on. And if I were to mess around with the implementation details of Fibonacci, maybe I will make fib 1, if fib equals n equals 0, equal 1, 0, return 1. Let me play around with this a little bit. Now let me just say, what if I want my second Fibonacci number to be, I don't know, 2? How does that change things? Oh, let's be more interesting. Let's maybe make our second Fibonacci number 3. Okay, so I've now broken up my base case into 2 base cases with different values. All right, now let's run through and see how this behaves. Notice I didn't have to touch test fib because I've properly abstracted all the implementations of Fibonacci are invisible outside of that function. All test fib cares about is being able to call fib. You'll notice I get a different sequence of numbers. So 1, 3, 4, 7, 11, 18, 29, so on and so forth. Of course, at the end of the day, I want to make sure I go back to my original base case where I just return. I'll make this easier to reuse. All right, let's make sure this all works right. All right, good. That was the last sequence we had. So again, one thing, once you've written the Fibonacci function and written things properly within inside the Fibonacci function body, I can go on to define other test functions. So one thing you might be curious about is, what's the ratio of these Fibonacci numbers as n goes to infinity? So here's a test function that does exactly that. I'll write a for loop, which steps through however many times as I want. And it tells me that the ratio of the I plus first and the ith Fibonacci number is, and then actually uses whatever numerical value that's produced by that division. And so just running this, maybe a little bit longer. Well, the first ratio is 1, then 2, then 1.5, then 1.67. Seems to start settling down to this 1.61803. Does that ratio have any significance? Turns out it does. And in fact, this is exactly what the golden ratio is. So several ways you can define the golden ratio, but one way is to just say, I'm looking for a ratio where if I take the ratio of the sum to the largest part in that pair of numbers, A and B, that's equal to the ratio of the largest to the smallest. All right, so instead of using equations, I'm looking for some numbers which satisfy A plus B divided by A equals A over B. And it turns out that if you fix these values for A and B, you try to figure out what that ratio has to be if this equality is true, you get the golden ratio, sometimes called phi. So this ratio appears in multiple ways. If you have a rectangle and you think of, let's say, the height as the shorter side and the width as the longer side, this is going to be a golden rectangle if I can divide and make another rectangle where now the width of this inscribed rectangle in ratio to the height of this rectangle is the same as the larger one. So it's this notion of self-similarity, but after we've rotated by 90 degrees. You also have probably heard that the golden ratio appears in all sorts of places, in biology, and patterns in leaves and seeds. And we'll highlight a few more examples of this. So just visually, what the golden ratio is it's a pair of numbers. What's the ratio of a pair of numbers where if I look at the ratio of A to B, so A divided by B, that's the aspect ratio of this pink or red rectangle. It's the same as the aspect ratio of A plus B to A. So A plus B being now the larger side. There are other places in which this appears. So if you take that same sort of golden rectangle and you start tracing out the corner of the far left edge, where I'm assuming I've got this longer base here, and then I take that, shrink, and rotate by 90 so that you get this same ratio behavior, put another dot there, and then you take that rectangle, and since it will also contain another subdivided rectangle inside of it, you rotate by another 90 degrees, and connect that with a dot there, and if you trace out this path, sometimes called a golden spiral. This image is kind of cute. Here's some other examples. This is a topic called phyllotaxis. So here I've got these nested aloe leaves, which have seemed to arrange themselves and grown in these interesting sort of spiral patterns. And the way in which these leaves arrange themselves actually tend to follow these golden spiral trajectories. earlier slide, I gave a link where you can read more. It's actually a good reason to think about why that's true. And then finally, nice to sort of, especially if you're a fan of Ramanujan, golden ratio can be expressed as a continued fraction, right? 1 plus 1 over 1 plus 1 over, and you just keep nesting inside of it. These are more examples of recursion. So you can see that golden ratio, which is this number which has been studied and the object of fascination for thousands of years, is also deeply related to this concept of recursion. All right, so those are just sort of fun examples and applications of recursion appearing outside of computer science. And I hope this has inspired you to maybe do a little programming your own and see what other patterns you can discover. All right, I'll see you all in class.